Hello, can you hear me?
Yes.
Oh, good. Okay. Um, you should see my desktop. Is that what you're seeing?
Yep.
Okay. I think I'll keep the video stream as my desktop so we can talk about code and examples and uh, and if anybody's got any questions, just anytime you want, just interrupt. Just because I wouldn't know I wouldn't know for sure if you had I don't think there's any way for you to raise your hand or anything like that. So if you have a question, just just
रिकॉर्ड कहाँ है इसमें?
pardon me?
दिख गया ना इस रिकॉर्ड?
Say again?
रिकॉर्डिंग करने पर मीटिंग हो मीटिंग में उससे रिक्वेस्ट करनी पड़ेगी रिकॉर्ड करने की.
Let's see. Okay. Okay. Okay, we're going to keep on talking about parsing. Okay, so we're going to look at the examples in this folder on parsing and grammars and parsing. So I've downloaded that here. Okay, and we're in this baby expressions. What we're really trying to do is learn to parse arithmetic expressions. Okay, so we're trying to build up to arithmetic expressions, and the two main things we have to deal with are precedence and associativity. So we're really building up to the idea of associative operators, left or right associative, and then the precedence of operators. Okay, so we started with just this. So we started with just a language of just one operator, addition. Okay, but we could make it left or right associative. So we talked about making it left or right associative by writing a grammar in a couple different ways. Okay, so that's what we did before break. Okay, then another thing we did was put parentheses in there. Okay, so parentheses let you group things, but they're not changing your precedence of anything. So this has only one operator, but it has parentheses. Okay, and again, you could make it left or right associative. Okay, so here was the grammar for, now this one has, see, it's right recursive, so that makes it right associative. Okay, so remember, right recursive makes the grammar right associative, and then left recursive makes the grammar left associative. Left recursion makes the grammar left associative. Okay, right now we haven't gotten to this. Let's start talking about this with two operators. Okay, right. So the language is this one. There's the letter A just represents, it could represent variables, numbers, okay, some kind of literal, but we have plus and multiply, and we could mix the pluses and multiply. Now there's no parentheses yet in this language. It's just a language of two operators. Okay, so you could use, but you can mix the operators any way you want. Okay. Okay. At this point, we have to worry about each operator, whether it's left associative or right associative, the two operators, whether one of them has higher precedence than the other. So it's as we go through the different grammars, we can try, the goal is to just do a bunch of different things with different left and right associative and different levels of precedence. Okay, so here is an ambiguous grammar because it's both left and right recursive. Okay, so an expression is any expression with a plus followed by any other expression, or any expression with a times followed by any other expression, or just a literal. Okay, okay, and that defines this language up here, but it gives it no structure at all. It doesn't make it left associative, it doesn't make it right associative, doesn't give any precedence, and it's an ambiguous grammar. You can't even really parse with it. So here's something that gets a little bit more interesting. Okay, here it's right associative, right recursive, so it's making the plus right associative, and it's making the multiplication right associative also. Okay, but this doesn't make either operator any more important than the other operator. Notice that you just parse essentially from left to right, and it doesn't matter if you come across a plus first or a star first. Okay, so let me see if I can give you some examples. Let me try sharing the whiteboard. Okay. Okay. Now, if you write A plus A times A, okay. So how's this parse? The grammar is just going to say there's an A plus something else. Okay. So the grammar is going to parse it as A plus, because the grammar always said start with an A. And so notice it doesn't matter if I write A times A plus A, it'll parse the same. It'll parse it from left to right. So we're looking at a language that is left associative. It parses from left to right, but it doesn't treat the plus or the times as any more important than the other. Okay, so that might be useful in some cases. That's sort of where plus and minus are like that. Plus and minus in regular arithmetic, you know, if you write A plus A minus A, you just do it from left to right because they have the same level of precedence. Okay, now let's see. I want to switch back to the desktop. Okay, so okay, now this isn't this isn't very hard to parse. You know, this is, if we look at the parsers, if we looked at here are the parsers over here. Okay. Yeah, there isn't a parser for language 8 because there really isn't. It isn't very hard to modify, say, the parser for language 6 to get language 8. Okay, you would just remember you write a get expression for each of these. This expression has 3 clauses. It's either this. Oh, actually, you can rewrite this in a more easy way. So if you're going to write the code for it, you would write this one as, for example, here. In all 3 of these cases, you always begin with an A. So if you notice, it's A plus expression or A times expression or A. So you always begin with an A. So the first thing you do is you grab an A. Then optionally, you look for either a plus or a times. It's optional because if you're in this case, there's nothing after the A. But if you're in the other 2 cases, after the A, there's either always going to be a times or a plus. Okay, so then you grab either a times or the plus, and then you recursively get expression. So writing the code for this would be get an A, then if there are more tokens, get a plus or a multiplication. So you're going to get one or the other, and then you recursively get another expression. Okay, so that would be the recursive descent parser for this. This function would get an A, then test it for more tokens. If there's another token, it matches either a plus or a times. If it doesn't match those, then there's an error. And then after it's matched those, then it gets another expression. Okay, right, right. Now, here is trying to switch to left recursion to make it left associative. Okay, so here it becomes a little bit trickier now because over here you always had an A on the left, and then after the A you had the optional something else. Now it's just a little bit trickier. You the recursion's on the left, so it's left associative. Okay. If you rewrite it, you would write it this way. There's an optional this stuff. Okay. There's an optional expression with a plus or times after it, followed by an A. Okay. But this is really hard to program. This cannot be written as a recursive descent parser. So we eliminate the recursion with a loop. Okay. So instead of writing it recursively, we actually write it as a loop. Okay. We say that the expression is an A. Okay. And then now this loop actually eliminates this left recursion. If you look at it, this thing is looping to the left, which is really bizarre. Okay, it's looping by saying there's an A on the right, and then you have a repeated number of these things going off to the left. That's actually hard to program also. So we end up programming it this way. It's just a string. You start with an A, and then you have a repeated string of pluses or times A's. Okay. But that line of code there is exactly this one up here. Remember, we talked about this a little bit last week. When we eliminate the right recursion, we get this. When we eliminate the left recursion, we get this, but this is actually unprogrammable. You can't iterate to the left. So we make it look like this, but then we have to write our code as a bottom-up parser. We have to write our code, when we iterate this thing on the left, we write the code instead of a top-down parser, it's a bottom-up parser. Okay, and you can kind of see it here. If you think about this, this tree is built first, and then it's tacked on to that tree, which is then tacked on to that tree there. And we're actually building it from the left bottom up towards the top, which is, the root is this guy here. Okay? Okay. Now, let me see if I can draw a picture of that. Let me try to draw a picture of this. Okay? Okay. So the expression was look like something like this. Oops, that's not what I wanted. Okay. A, say, plus A times A. Okay. Okay. Now, the parser is going to find the first A. It's going to find the first A and build a tree out of it. So it builds, this is the tree. Okay. But then the parser says, oh, and then I see there's another plus A here. Okay. So it's going to say now I have to build another tree. My old tree goes on the left, and then this guy goes on the right. Let's see if I do this right. Okay. Then it sees this star, and it says, oh, now I'm going to have to build a star tree where my old tree is on the left. So my left, see, I'm building from the bottom up. This part becomes the left, and then I have the A on the right. Okay. Now, if there was another plus A here, then it would just keep iterating across. Now, all of this is here. That's going to be pushed down. There's going to be a new tree here. All that stuff goes over there, and then the A gets put here. Okay, and then I could keep iterating across. If there was another star A here, yeah, as I'm parsing across this, I say, oh, another star A. So the star is now the new root of the tree. The previous tree is the left branch, and then this is on the right. Okay, so now it's parsed it as A plus A times A plus A, you know, times A. Right? Did you write that right? Okay. So it's parsed it as if it was left associative. By it goes across from left to right, but it works from the bottom up. This was the first tree. That was this guy. Then plus A. So you saw the plus A, so that built plus A. Then you see the times A, so that took everything over here, put it over there, and then this is the times A. Then it sees plus A, then that put this one here. So see, that was the iteration. A plus A times A plus A times A. Okay, so there was the iteration. Now let's see, go back to the grammar so we can see it. Yeah, there was the iteration, and look, we go back to the grammar. See, we go back to okay. There was the initial A, and then you iterate plus A, either plus A or times A, plus A or times A. So we iterate from left to right, building the tree from the bottom up. Okay, and that's done not with recursion. In the code, that would actually be done with a while loop. Yeah, you would, while there's still more tokens, you would just grab another plus A, take the current tree, put it on the left, put the new A on the right, then see if there's, then loop again. If there's more tokens, take the current tree, put it on the left, take the new A and put it on the right of the tree. Okay, so so what's in our way of doing this, left recursion becomes a while loop. Left recursion is left associativity, but it becomes a while loop. It actually isn't going to be implemented as recursion. Okay, all right. Now, here's something that's trying to be different. Okay, here's an ambiguous grammar that's right recursive on the plus and both left and right recursive on the multiplication. So it's making plus right associative and multiplication not associative. Okay, but it's ambiguous, so it's not a very useful grammar. Okay, but the grammar is saying, the grammar is saying that A is right associative and I'm sorry, that multiplication is right associative, and I'm sorry, that addition is right associative and multiplication is not associative. The grammar is saying that, but you can't write a parser for this grammar because it's ambiguous. Okay, so the grammar does say it, so that makes it, the grammar is not in a sense incorrect, but the grammar can't be really implemented as a recursive descent parser. And you can't really do much parsing with it because it's ambiguous. Okay, all right. Now here's another attempt at something interesting. Okay. This one makes multiplication right associative and addition left associative. Okay. Okay. This actually changes the language. This thing looks like it would be okay, but it actually isn't. It is no longer this language. Okay. Let's see if we can see why. It actually is no longer the language we started with. Okay. It looks like it would be. It looks like, oh, I have a multiplication and addition. Multiplication is right associative. Addition is left associative. Okay. But it actually, something's gone wrong. Okay. Okay, let's take a little bit, like, look at that string there. That string, should be in our language, A plus A times A, but it doesn't parse. Okay, so try to parse it. Okay, so use this grammar to try to parse this. Okay, so we start with an A, but we're not this, because that case is only an A. Okay, so now, oh, we could be this, or it could be this. You know, we have to look carefully. So we have an A here. That this A could be that A, or it could be that this A is that expression followed by a plus. Okay, so we can try to, now if this A is that A, the next thing has to be a star, but the next thing here is a plus, so it can't be this one. Okay, so if we want to parse this, it won't parse with this guy, it won't parse with this guy, so let's try to make it parse with this one. Okay, all right. We would need an expression plus A. Well, we have a plus, but to the right of it is an A, but there's more stuff to the right of that. So if we try to match this, we would have to match that A with expression, that plus with this plus, that A with that A, but then we fail because there's stuff left over that didn't get matched, so this thing did not parse. Okay, so no matter what we try, we can't parse it with this, we can't parse it with this, and we can't parse it with this. So it turns out this grammar doesn't do that. This grammar doesn't include that sentence, which actually brings up the weird question of what's this a grammar for then? You know, it looks like it's going to be a grammar for this language where you make plus left associative and multiplication right associative, but it turns out it isn't. Okay. Okay. I'm trying to remember. I don't even know if I remember what this is a grammar for. I think it works out to be only, it's the grammar of strings that are either all multiplications or all additions. I think that's what it works out to. A string in this language is got only multiplication in it, which and then they're right associative, or they have only additions in them and then they're left associative. But you can't mix the addition and multiplication. Okay. Okay. Notice that gives us a feeling that it's hard to mix left associative with right associative. We're going to see that that's actually kind of a general case, that if you mix left associative and right associative operators, they have to be at different levels of precedence. They actually can't, like this case, we're trying to make this operator and this operator the same level of precedence, but different associativity, and it's not working. You know, our language changes from this language to a language of only additions or only multiplications. Okay, so notice that this is kind of weird. These little pieces here look okay, like that little piece there and that little piece there. They look just like the little pieces up here, you know, and they look like the little pieces up here. But the thing is, when you start mixing these little pieces, they don't mix as easily as you think they do. Like here, that and that are fine. Okay. Here, that and that they're kind of fine. They don't work well the way you think they would. You know, they do define a language, but it's not as obvious to us what that language is. Okay. So grammars are tricky things. When you put together a grammar, it's not unusual for grammars to have unintended consequences. You write a grammar and you think you understand what it does, but then as you play around with it a little bit, you realize the grammar is trickier than you thought it was. So this grammar is kind of tricky. It does make this guy right associative, does make this guy left associative, but it prevents us from mixing them. You know, when we make them left and right associative, now our language has strings of all these or all of these, but not mixed. Okay. So how can we mix addition and subtract? How can we mix addition and multiplication in a way that how can we start getting things where, well, first of all, we'd like actually to have different levels of precedence, and we might like to also have them one be left associative and one be right associative. So what we're going to do is first we're going to tackle the precedence. Okay. So here we're going to make multiplication have higher precedence. But notice that we're going to have to do it by coming up with two pieces to the grammar. Okay. So here's now what the grammar looks like. An expression. Okay, this one's ambiguous. Notice that plus is neither left nor right associative. Well, it's both left recursive and right recursive. And this thing called term is also left recursive and right recursive. So what we have here is an ambiguous grammar that makes multiplication higher precedence than addition. Okay? So it's not really a useful grammar because it's ambiguous, but it shows us our first step of getting precedence, of somehow meaning that you do the multiplications before you do the additions. Okay? Okay? Now, like, let's parse a string. Okay? Let's parse that string here. Okay? Okay. Let me put this in an editor. It'll be easier to work with if it's an editor where we can change it. Okay. So here's our let's take this. Let's try to parse it. Okay. So we go up here and we start looking at what an expression is an expression plus an expression or a term. Okay. Now here I have expression plus expression. I could do expression plus expression. I could do expression plus expression. Okay. Okay. Right. So I have two choices there. Now notice this is, or I can do term. Now, if I drop down to term, I could say, oh, this thing is term times term. So I can parse this thing three ways. See, it's ambiguous. I can parse it three ways. So I could parse it starting with the plus with an A on the left. Okay, so that's I can parse it starting with an expression plus an expression. So then that'll put all this on the right. Okay. Now, if I put all that on the right, okay, how am I going to parse this? Well, I could parse it as a expression, plus, okay, it's a plus with a on the left, okay, so plus with A, and then it's a term on the right. Okay, see, now the expression is a term on the right, so over here it's going to be a term now. Okay, and then that term is going to be times, and then A and A. Okay, so there's one way to parse this thing. Okay, that was parsing this guy as the first one. Okay, let's try parsing it a different way. Okay, we could parse this thing here as expression. And then this plus here is the second plus. So if we parsed it that way, my root plus has this on its left. Okay. Right. So that was this plus with an expression on the left that is A plus A, and then it'll be an expression on the right, but the expression on the right is going to be a term. See, when I parse this part here now, the expression on the right will have to be a term, okay? So then on the right, I'll have to have a term, which is times, and then that times will have a and an A and an A, okay? Okay. Okay. So I see it's an ambiguous grammar, so I can parse this thing multiple ways. Now, notice that the times is getting pushed down. Yeah, the times is lower in the parse tree. This is the idea that the multiplication has higher precedence. Yeah, the times is getting the by making the times a subproduction of this guy, you're essentially pushing the times always farther down in the parse tree. By pushing it farther down in the parse tree, it gets evaluated first. So the lower part of the parse tree, when you evaluate the parse tree from bottom up, so the things that are lower get evaluated first. So this guy's got higher precedence. Okay, so in a sense, it's kind of vague still, but this one's got a higher precedence because it keeps getting pushed down to the bottom of the tree. Okay, all right, but this is ambiguous. So we want to do this in a better way. Okay, we really don't want to work with ambiguous grammars. So let's look at the next grammar. Okay, okay, so okay, yeah, and we're going to stick. Okay, this one's still ambiguous. Okay, here's another ambiguous grammar that gives, again, star gets higher precedence. Okay. Okay, it makes plus right associative and doesn't make star left or right associative. Okay, so this one's kind of weird. Okay, expression is a term plus an expression or a term by itself. And a term is a term times a term or just a literal. Okay. Okay. Expression is right recursive. Term is both left and right recursive. So it's not got an associativity. Okay, and that's why the grammar is ambiguous, because this part here is still, notice that what we've done here, this was ambiguous and this was ambiguous. Now we've got this one not ambiguous. Expression is right recursive. Term is still ambiguous. Okay, all right, so that's still not the grammar we quite want. Let's look at another one. Okay, here's another one that, okay, still ambiguous. Idea here is there's lots of ways you can play around with these grammars. Okay, notice that you can, here I made term ambiguous and expression not ambiguous. Here, oh, the only thing is, I'm sorry, the only thing that's changed here is that expression is left recursive. Yeah, so it's really the same grammar, very similar grammar. Here, expression was right recursive. Here, expression is left recursive, and term is still not recursive. It's doubly recursive. Okay, so it's multiplication has higher precedence. The only difference is this one plus is right recursive, and this one plus is left. Here plus is right associative. Here plus is left associative. Okay, so both of these are very similar grammars. Neither one is really what we want. Okay. Okay. Now here we switch to making term associative and plus is still ambiguous. Okay. So here I switch from, up here I made expression the associative one and term the ambiguous one. Now I see, well, okay, I can make expression the ambiguous one and make term the associative one. Okay, so now multiplication is left associative. Okay. Okay. All right, so there's a, but none of those are really useful grammars because they're all on the ambiguous side. The real point of these is just show you how many different ways you can write a grammar. And it's, it takes practice to see how some of these are useful and some of them aren't. When they're doubly recursive, they're really not that useful. They do get used in a few places. There are situations where a doubly recursive grammar like this could be useful, but not very often. For most of the time, you do not want ambiguous grammars. Okay, so here's another one. Okay, this one is not ambiguous. Okay, this one should work. This one would be one we could use. Okay, multiplication has higher precedence because it's down lower in the productions. Expression is left recursive. Multiplication is right recursive. Okay, so we should have addition has lower associative, addition has lower precedence than the multiplication. Addition is left recursive, and multiplication is right associative. Okay. Okay. Let's parse one of these. Okay. Let's parse one of these because it's a little bit interesting to see. Okay. Let's parse this one here. Okay. Okay. Now, if we just think about it, we can think about how it's going to parse. Okay. Multiplication has higher precedence. Okay. So that means you group this before you group the other ones. Okay. Okay. So we would know that this thing would be lower in the parse tree. Okay. So now, but then the question is, which one of these pluses is higher? See, after you group, you think of this, you would think of it as having parentheses like this. Now you got A plus this thing. Well, is the plus is done from left to right or the plus is done from right to left? Okay, plus is left associative. So that means we do this plus first, followed by this plus second. Okay, so the pluses are left associative. Okay, so then that would end up being parsing as the first plus with an A, and to the right of that plus is another, another plus. Okay, and then to right of that plus is to the left of that plus is an A. But on the right of this now is the times of A and A. Okay. So now we just parsed that by thinking about it. What if you use now think about using the grammar to parse it. Okay. So we parsed it just by using the rules here. The grammar has this higher precedence and plus is left associative. Okay. But let's actually parse it by the grammar. Okay. So an expression is a term followed by plus term, plus term, plus term, plus term. Okay. A term is an A with an optional multiplication of another term. Okay. Notice I've eliminated the recursion. Notice the expression is no longer recursive because remember when we talk about left associative, we ended up in the other example, left associative ended up becoming iterative, not recursive. Okay, so if you see here, expression now has been unrecursed. It's just iteration. Okay, and term is right recursive. Okay, term is right recursive. Okay, so in this case, we have to parse it as an expression is a term. So first we have to find a term. So we're parsing this guy, and first we have to find a term. Okay, so a term is an A. Okay, there's an A, followed by multiplication by a term. Okay, let's see. No, that isn't part. Let's see. Oh, I'm sorry. Expression is a term. Okay, so we have to find a term. A term is an A. Okay, there's our A. Okay, and then an optional, but see, we don't have that optional. So we just stop there and say, that's our term. Okay, so term is A. There's our term. So that term with that A. Okay, so now we do a plus term. Okay, so now we're going to do a plus term. And we do the same thing again. This term, we go down here, a term is an A with a possible star after it. But this A doesn't have a star after it, so that term only is the A. Okay, so now we've got the plus A plus A. Now we do another iteration of plus term. Okay, that's this third plus. So now this term down here becomes term A, and then there's the star term. There's that guy there. So the third time we hit on the third time we hit term, we actually found A times term. The first two times when we did term, we found A without anything next to it. Okay, so again, expression was a term. So we start off, we have to parse this thing by finding a term. The term is an A. Okay, there's the A, followed by a star. Oh, no star, so we stop with the A. So we just stop A, that stops this term here. That's our first term. Okay, then we do one iteration of plus term. So there's plus, there's term. Again, and that term is just going to be the A. Okay, then we do our second iteration of plus term, plus, and then the term now becomes A star A. Okay, all right. So that's what it looks like actually using the grammar to parse it. Remember, we parsed it two ways. One was just thinking of the rules. A is left associative and star has higher precedence. So we were able to draw this parse tree. And then we parsed it using the grammar. I should have drawn, if I had a nice way to draw, I could have shown you how I was building the tree. Think about it carefully. When you build a tree this way, it's bottom up. So this term here was that tree there. Then when you did the plus term, you did from the bottom up. That created, no, I'm sorry. That created, no, real carefully. Let's see. Oh, no, it's not quite bottom up. Let's see. This term is that A. Okay. Then you do the plus term. Okay. So that's the plus. Am I reading this right? Yeah. And then this term here would be yeah, it's tricky. I'm getting mixed up now in building the parse tree from the grammar. Oh. Does everybody see what I did wrong? Does anybody see? Notice that plus is left associative, right? Okay. So this should have been A plus A first. I didn't draw the right parse tree down here. I didn't quite draw the right part. That's why when I tried to use the graph, I didn't quite draw the right parse tree. Okay. Okay. Let's finish putting parentheses in this thing. Okay. Multiplication has higher precedence than addition. So there's the first set of parentheses. Okay. But then addition is left associative. So that means you should do that addition first, right? So that means that there should have been parentheses there and there, all right? Okay, and then you do that addition. Okay, so left associative means you would do that addition first, and then the result there would get added onto this. Okay, right? So I didn't draw the right parse tree. So the parse tree should be okay. See if I can draw. Let's see. Make a little bit more room. I think that's it now, right? Okay. Oops. That should be the right parse tree. Okay. So we started with A plus A plus A times A. And we grouped it that way. Okay. Right. So plus is left associative. Multiplication has higher precedence. So this plus here is the last one done. That's this one. This plus here is the first one done. That's this one. Okay. Now go back over here and start parsing it from here. It makes sense now. It should make sense now. Okay. An expression is a term. Okay. So that's him. Expression is a term. Okay, that's a term is an A. There's nothing following. There's no multiplication following that A. So that guy's a term. Okay. Then, so he becomes term. So he's he's a tree by himself. That A is a tree by himself. Okay. Then after finding the term, you do plus term. Okay. So that would be plus term here. Okay. So that would be you're going to form a tree with a plus on the root, okay, and a term on the right, and a term is A. So that's this tree down here, okay. That tree is, so there, that plus is that guy, okay. That A is that term, and that A is that term. So that's one iteration of the plus star, okay. All right. Then you're going to iterate it a second time. Okay, so after now, so now we're doing this iteration of plus star. So we find that plus, That's this one. And then we find this term, okay? Now, this plus is that one. We're building up from the bottom up, so our previous tree is on the left. Our previous tree is on the left, and on our right is this term, okay? Then this term is an A. That's this A. That's down here. A star. That's the star, the root, times another term. And that term is the last A. Okay, so that goes here. All right, so then we can parse it by parenthesizing it. You know, take this string, put parentheses in it using these rules. Star has higher precedence, plus is left associative. So then if you use those rules, you get these parentheses. Then the parentheses help guide you that this becomes this branch down here. This guy here is the root of the tree, the last operation done, and this part here is this here. And then if you go through here and parse it bottom up, you'll build this tree, tack it up to here. You'll build this tree, make him the left branch of this, then you'll make this the right branch. Okay. Parsing's weird. Parsing can you read, it's a weird kind of code. You read this code, and what it is you, as you process the string, reading this code, you build this data structure. Okay, so you process this code, you process this string from left to right, and you look at these rules to help you figure out how to build this data structure. Okay. All right, let's go back to the next grammar. Okay, so now we have, yeah, I mean, you can do the same with all these examples. You can work through each one of these examples, parsing them. You know, and again, you can parse them by using parentheses, by saying, oh, what are the rules? Think about adding parentheses, and then you could figure out how to parse it. Or you could also practice parsing by following the parser grammar. Following the grammar and think about how you parse one of these strings by the grammar. Okay, let's see. Should we do another one? Let's try doing this one. Let's just see if it, let's parse this one. Okay, first, if we parse it the easy way, we use parentheses. We know that the multiplication has higher precedence, so we would group those two together, and we group those two together. And then there's the plus in between. Okay, so that means that's pretty easy to see how that's going to parse. We have this plus at the root, and then we have two trees identical underneath it. We have two multiplication trees underneath it. Okay, and there's just an A here, and an A here, and an A here. Okay, so that's pretty easy. Okay, so that's by using the rules that we know that this grammar makes multiplication higher precedent, and we're not even using the fact there's only one plus, so we don't need to use the fact that plus is a left or right associative. Okay, now let's try parsing it using this though. Let's go through this guy using this. Okay, so an expression is a term. Okay, so we go down here, and expression is a term, and a term is an A. Okay, there's our A. There's our A. Okay, but a term is an A with an optional times term. Okay, there's a times there. Okay, so now, is there a term there? Okay, and then term is an A possibly by itself. So this term is an A times a term where this term is just an A. Okay, so that parsed this piece here, that parsed this piece here. Okay, so that means this guy here is that tree right there. Okay, all right. Then we get to the plus. Now we do the bottom up part. We take the term, put them on the left of a plus, and then parse the term that comes after. Okay, and we only have to do this iteration one time. There's only one plus, so we only do this iteration one time. Then this term parses exactly the way the first one did. This term is going to be, it's this A times another term, and then that last term is just that A there. Okay, right? So the multiplications have higher precedence than the addition. So that one was more straightforward. Okay, so you can do examples. You know, you can take any one of these examples and parse it by thinking, how would I parenthesize it using the rules of the expression? But then you can also make sure that you can also parse it by following your way through the grammar too. You should get the same parse using these rules as you get by following this grammar here. Okay, let's see. Now let's look at another grammar. Okay. Okay. What do we change here? Oh, we didn't. Actually, we probably should do one more up here, because notice that star is left associative, addition is left associative, multiplication is right associative. We didn't actually see that. Now, to see that, we'd have to do something that has 3 stars in it, like this one has more than one star in it in a row. Yeah, it has to have more than 1 star in a row. See here, the one we did here has 2 stars, but they're not associative because they have a plus in between them. So this star doesn't associate with that star. But here, these 2 stars are in a row. So those 2 operators in a row, so that you have to do an associativity with them. So let's do this one. Let's do this one last one. Okay, so let's parse that one. These are little exercises. They're nice little exercises. Okay, all right. So there's the expression. How do we parenthesize it? Okay, the rule is that multiplication is right associative. So that means you would do that multiplication first, and then you would put an A star on the left. Okay, so out of these 3, since it's right associative, you do the right hand multiplication first. Then all that has higher precedence than the addition, which comes last. Okay, so that's what it would look like with parentheses. Okay, so using the rules, I can parenthesize it. That tells me how to build the parse tree. The parse tree is going to be a plus with an A on the right. Whoops. Okay, now what's on the left of the plus? Okay, now I have to be careful. What's on the, what's this parse tree look like? Okay, this parse tree has a product here. It's got a product there. There's a single A on its left, but on its right, it has a product of A with another A. Okay. Okay. So we look at this, and first we just parenthesize it using the rules of the language. So from the grammar, we know that the multiplication has higher precedence, and the multiplication is right associative. So that means we do all the multiplications first. Okay, so that's this outer group of parentheses here that said do the multiplications first. But then the multiplications are done from right to left because the multiplications right associative. So multiplications are done from right to left. So then the parse tree looks like this. Okay, now what about parsing this using the grammar? Okay, see how, okay, let's parse it using this grammar. Okay, all right, so an expression is a term, okay? And a term, okay, expression is a term. A term is an A followed by multiplication with an optional term. So there's A multiplication with another term, okay? But now this term's going to be bigger than it was before because now we've gotten through A times, now we have to find another term. We're going to pick up that term there, okay? So this term, so expression is a term. That term is going to be this whole thing, actually. See, that term is going to be, term is an A, that's this guy, times, that's this guy, and then another term, and that term's going to end up being those three characters, okay? Right? And then how's that parser going to build that, okay? The expression will say term. So it's going to build a term tree. So we're building a tree. This is before we do the thing on here. So we're building this tree here. How do we build this tree? We build this tree by finding that A. That A is that guy. Okay. So that guy is what is going to be the left branch of our tree. The root of our tree is that star. Okay. So there's the root of our tree. That first A is the left branch. That star is the root of the tree. Then on the right branch of the star is that tree. And that tree is going to be, go back over here, term. Then it's going to have a star with an A on the left branch, and then another term, which goes back around to be just an A, okay? It's a little bit trickier here. We're using recursion. Now we're using recursion. Down here, we're using recursion. We're saying that the tree is A on the left branch, star is the root, this is the right branch. A, star, right branch. And then again, but then when we recurse again, it's going to be the same. A, root, right branch, but that's this part down here, which becomes the right branch of this one over here. Okay? Okay, so notice that the grammar made multiplication right associative. Okay, so these guys in this expression, these two were multiplied first. Whereas with addition, addition's left associative, so over here, that addition got done first. The left addition was done first, but the right multiplication is done first. Okay, so the grammars are doing their job. These rules are making things work the way we want them to. Okay, all right. Now, go back one more. Oops. I'm sorry. Where are the grammars? Okay. There was one last grammar here. It does a minor little difference. We're still making multiplication higher precedence than addition. Okay. Now addition is left associative and term is left associative. Multiplication is left associative. So they're both left associative. Now this is actually kind of messy because that means that neither one are recursive anymore. So now everything's turned into iteration. Everything gets turned into iteration. Left associativity, which is left recursion, becomes iteration. Okay, so these get parsed using a while loop, not using recursive functions. Okay, and you can go through notice that these are the exact same strings here and here, but they'll parse differently. So you can do every one of these again. Yeah, it's a nice little exercise to do them all again and see how they parse to different parse trees. This grammar will parse them differently than this grammar did. Okay, so that's the kind of practice that's the kind of interaction you do with a grammar and a language. You follow the grammar and notice you can do this with baby expressions. When you have a 20-page grammar like the Java grammar, you don't really do this. You might work with little pieces of the grammar at a time, like what's the grammar for an initialization? What's the grammar for a for loop? What's the grammar for a while loop? But here, we can just concentrate on one little piece of the grammar, and we can analyze how it takes simple strings and builds the parse trees. How we can go from simple strings to their parse trees. Okay, now this language was 2 operators. Okay, we've got the operators so that we could give one of them higher precedence than the other. We can kind of mix the associativity. Once the operators have different precedence, we can give them different associativity. So that's one of the important things we saw. That notice this one has left and this one has right. When they did not have different precedences, remember we couldn't do that. When 2 operators have the same precedence, you can't give them different associativities. But when they have different precedences, then they can get different associativities, or if you want, you can make them both left associative. But you have your choice. You can make one left associative, one right associative, or both left or both right. Okay, all right, now let's look at another. Okay, that was the 2 operators. Okay. Here's more detail about this example 11. Okay. Remember we said that this one changes the language. So this page here just does that one in a little bit more detail. Okay. It just does a little bit more detail with that example of why this thing doesn't parse here. Okay. And then it asks, what does this language look like? Okay. If you take this grammar and rewrite it, here's an example of what the grammar can be rewritten to. Okay. So if you play around with this, and an expression is, notice expression is one of 2 things. It's this or this. Now notice that a term doesn't go back to expression. So if an expression is a term, then that's a whole different thing. You don't go back to expression. They're not mutually recursive. Notice that expression uses expression or term, and term doesn't use expression. What that means is the language breaks up into 2 pieces. It breaks up into a bunch of additions. Okay. So any given string in this language has only additions, or it's a term which has only multiplications. So this is the thing that lets you see that what this language is really doing is saying that it's not strings that use addition and multiplication. It's strings that use addition or use exclusively addition or exclusively multiplication. Okay, so you kind of see that here. Because there's no mutual recursion here, you have strings that use only the addition, and you recurse on those as many times as you want, or you have things that only use the multiplication. Okay. All right. So that goes through a process. There's a little bit of like grammar algebra here to show you how you can take this grammar and rewrite it and see that it really breaks down into these 2 production grammar, which says that this language has only got additions or only got multiplications. Okay. Right. Now here's actually what our goal is. 2 operators and parentheses. This is pretty much regular arithmetic. So this builds up pretty much regular arithmetic. So it's okay. Okay. First, we just do like we did before. Start with ambiguous grammars. Okay. So we want a plus operator and a multiplication operator. Here, there's no precedence. An expression is either an expression using addition or an expression using multiplication or expression using parentheses or just a term. So this is letting you mix and match additions and multiplications all you want. There's no left associativity, right associativity, or precedence. Okay, so that's like a real simple grammar for our language, but it doesn't put any structure on the language at all. Okay. Okay. So now let's start the process of trying to put structure. We'll try to make, what we'll make is we'll make multiplication higher precedence than addition, though parentheses will have higher precedence. Parentheses will have the highest precedence, then multiplication will have the next higher precedence, and then addition will have the next highest, the lowest precedence. And then we'll do various mixtures of left and right associativity. Okay, so here, this guy's right recursive, this guy's right recursive, so they're both right associative. This gives them associativity, but no precedence. Okay, notice that there's only one production, and that production can use either plus or multiplication. So the parentheses have higher precedence than anything else, but the addition and multiplication don't. Okay, right? So this is it's an unambiguous grammar. Okay, and it makes operators both right recursive, right associative, and it just doesn't give one higher. So this would be what you'd use if you did multiplication, and this would be a grammar for things like multiplication and subtraction. Addition and subtraction. This is what you would get with addition and subtraction. Addition and subtraction have the same precedence, and they should be both left associative. Okay, so this is what you would do with two closely related operators like multiplication and division or addition and subtraction that are supposed to have the same level of precedence.
So, do you need like multiple productions to control precedence?
Yes. Yeah, always. It's always going to be the case that to get multiple levels of precedence, you have to have multiple productions. Yeah, you can't do it in a single production. It's a weird, like, I don't know if anyone has a proof why that is. You think, oh, maybe there's some real super clever way to write a production so that they have precedence. And as far as I know, no, that can't be done. You have to have multiple productions to get multiple precedence. Okay. Essentially, it kind of makes sense because higher precedence pushes you lower in the parse tree. And by having multiple levels of productions, you're essentially pushing things lower in the parsing steps. See, if you have only one production, there's only one level of parsing. So that means everything's at the same level in the parse tree. So you wouldn't be able to push something lower. So you can do it with parentheses, though. See, the parentheses push that lower in the parse tree by putting this grouping here. So yeah, with one production, I can make things inside parentheses have higher precedence, but I don't know of any way, and I don't think there is a way to make operators have different levels of precedence. Okay, right. So here's another grammar. Let's see. This one, they're both right associative. Here, they're both left associative. Okay, right. So addition and multiplication are both left associative. Parentheses has higher precedence. Okay. This is going to be turned into all iteration. Remember, left recursion is going to have to be turned into iteration. So notice down here, there's recursion still because of the parentheses. Okay, so it's not purely iteration. Let's see. oh, I didn't write out the, oh, this one doesn't need iteration because of a weird trick. Okay, the expression is, oh, there's a misprint here. Expression is a term. There's no definite, I think this is supposed to be term here. I think this one here is supposed to be term. Yeah. Okay, so expression is a term followed by addition or multiplication of an expression. So there's recursion. I have to look at this one carefully. Here there's left recursion. Here there's right recursion. So I may have messed this one up. See, that one looks like right recursion. So I may have made a mistake. I may have copied and pasted this from the wrong place. Okay. So grammar 19 is right associative. Grammar 20 is left associative. So that's the only difference between them. But I may have got these grammars not right. I have to think about that, because it looks here like this one's all of a sudden become right recursive, and it shouldn't be. Same here. This one, well, and this one should definitely be term. So there's a misprint here. Okay. Let's look at 21. Okay, now we go to two productions. Okay, so now multiplication, since it's lower in the productions, it has higher precedence. Okay, but this one's really ambiguous. So there's no attempt here to make things left associative, right associative. So, you know, we have parentheses and we have two levels of precedence, but it's ambiguous. Okay. Okay, here's one that's, again, still ambiguous. It's ambiguous because term. See, the addition is right associative, but term is ambiguous because it's both left and right recursive. Okay, so there's all these different, so you can kind of just keep doing the same thing over and over again. You can just create ambiguous grammars where you have mixture of left and right recursion. Okay, so this one's ambiguous, this one's ambiguous, this one's ambiguous. Okay, this is another one that's ambiguous. Just like before, there's a bunch of ambiguous ones, and they're just mixing. They always have some left recursion mixed with right recursion. So here there's left and right recursion. Okay, here there's left and right recursion. Here it's in the term, here it's in the expression. Okay. Okay, so here's one that's unambiguous. Okay. I wrote all these out. It might seem weird to just write out all these ambiguous ones. And I meant that to show that how you have to be careful. There's lots of ways to write the grammars. Some work and some don't. Yeah. And you're really looking for, and they look kind of like they would all work. Yeah. It doesn't look like this is inherently wrong. Yeah. And there's lots of ways to write these ambiguous grammars. And what you're actually, in the real world, people struggle when they're trying to write a grammar for a real sophisticated language, is to try to get their grammars not to stumble into these ambiguous cases, because there's so many of them. Yeah, I kind of repetitiously showed you all of them to kind of point out that there really are a lot of them. And when you're writing these grammars, it takes some real work to get a grammar that's not ambiguous and does exactly what you want. Okay, so finally we get to an unambiguous one. Okay, and it makes multiplication higher precedence. Now notice we finally have three productions. Okay, to get rid of all these ambiguities, turns out that we actually need three productions, and it kind of makes sense because we actually have three levels of precedence: multiplication, addition, and parentheses. Okay, so finally, to get to an unambiguous grammar, we end up needing now three levels of productions. Okay, expression, term, and factor. And in fact, these words I'm using are ubiquitous. Let me switch back to, notice I'm using the word expression, term, and factor. Let me switch back to the whiteboard, just remind you of something from calculus class. If you write something like a polynomial, like 3x squared plus, it's hard to write with a mouse, 5x y. Okay, there's a polynomial. This is called a term of the polynomial, and this is a term of the polynomial. So this is a polynomial with two terms. The terms are the things that are separated by pluses. So that's the language that's used all the time in calculus, and that's what people use in their grammars. The term production is essentially the thing that's building up, the thing that goes between the pluses. Then over here, in this term, there's two factors. 3 is a factor, x squared is a factor. In this term, there are three factors, 5x and y. Similarly, like if you take a number like 12, you know that number 12 is got two factors. Well, it's actually got three factors. It's 3 times 2 times 2. Okay, those are the factors of 12, 2, 2, and 3. Okay, so factors are the things you multiply out to get something. Terms are the things you add together. So that's terminology that's been around in algebra and calculus forever. So a polynomial is a sum of terms. A term is a product of factors. So and everybody uses that in their grammars. The productions in their grammars always use the word factors and terms. Okay, so term, remember, a term is a thing that's going to be added up. So see, an expression is a sum of terms. Essentially what this is saying is an expression is you add on terms, and then a term is a product of, well, factor and terms. Okay, notice a term is a product of a factor and a term. The idea being like if you have 3x squared, it's 3 times x, well, like say 3 times x times y. So that'd be 3 times the term, which is x times y. So then you kind of break the term up as, term is a single factor times the rest of the term. Then the rest of the term will then be a factor times the rest of the term. Or it could be a factor by itself, meaning that it's a literal or an expression. Like, think of, actually do it here. Here's a single term. Okay, there's a term with three factors. There's a term with one factor, another factor, and another factor. One of the factors is a grouping. Okay, if I take away the parentheses, now it's not a single term. Now it's two terms. That's one term and that's one term. Without the parentheses, then the precedence of the multiplication takes over. Okay, so this is a sum of two terms. This is a term with three factors. Okay, so in our grammar, a term is a factor times another term, or just a factor by itself, and a factor can be a grouped factor. Okay, so a factor can be You notice that down here, a factor is either something by itself or a grouped factor or something by itself. Here was a literal number. This was a group factor. This was a variable factor. Okay, so a term is a product of factors. So a term is a product. Actually, a term is a product of a factor times a term, a factor times a term, and a factor is either something by itself or a group of. Okay, so we have 3 productions now. Okay, notice how things things get a little bit more complicated. At this point, to have 2 operators with 2 different levels of precedence and parentheses, we need 3 terms. To give you a sense of how crazy this gets, remember that the Java language has 17 levels of precedence. Okay, I think I even put a, oh no, yeah. Here's I put a link in there. 16. Oh, this guy's showing 16. I thought it was 17. He's showing 16 levels of precedence. Okay, so you can imagine what the grammar for this looks like. There's 60. An expression. The grammar for that will be an expression that has to have 17 different things down here because you have terms and factors. And I don't even know what words they cook up to explain, because they have, they'll be defining the grammar of an expression, and they have to have 17 levels of precedence. So they have to have 17 different productions for all this. Maybe later on we can actually look in the Java, because the Java grammar is in the Java language specification, maybe get a sense of how they do that. Okay, but you can notice that one of the things they're trying to do is set the precedence. So there's 17 levels of precedence. Set the associativity. Now notice that there's 3 associative. Excuse me. We're gonna do this. You could be left to right. Now he says left to right. Left to right, I think, means left associative, and right to left means right associative. I'm not sure why he says right to left and left to right. Usually that's not the way people say it. Well, it's something. I mean, you do the operations. If it's left associative, you do the operations from left to right. But then there's a third possibility, not associative. Some operators, you're not allowed to use the operator without parentheses. So the operators can be left associative, right associative, or not associative. And see, in Java, the unary increment operators are not associative, and also the Boolean, the relational operators are not associative. Notice that means something interesting. You can't write this, which every freshman Java student wants to write. You think about it. Everybody in Java, if in their first year of Java, wants to be able to write something like this. I want to say that X is a number between 0 and 1. Okay? You're allowed to write that in calculus. X is greater than 0, less than 1. But you can't write that in Java because the relational operator's not associative. Because it's really going to, it has to group these. And what this is really supposed to be saying, because what you're really trying to say there is that you're really not grouping this. This is not an associative operation. You're really saying X is greater than 0 and X is less than 1, which is, so in Java, you really have to write this like this. You can write it that way. Okay. So Java prevents you from writing things. Now notice that they make it so that this will not parse. They don't do something dumb like compare X with 0, get a Boolean, and then compare the Boolean with 1. C would do it that way. I'm actually not sure what C will do with this. I forgot how C handles this. It might actually compare X with 0, get a Boolean, then compare that Boolean with 1. And since a Boolean is just a number, it could do this. It could just do this from left to right. Though it might be that in C, I actually don't know. I don't know if the relational operators are associative in C or not associative. It'd be easy to do a little test. But in Java, they made them not associative so that this wouldn't parse. You're just told that that doesn't work. Okay. And then you have to know to turn it into something like that. Okay. So we want to see how to do that. We want to see, how do you do that in your grammar? We've seen how to make it left associative. We've seen how to make it right associative. Left associative is left recursion, right associative is right recursion. We haven't seen yet how to quite make something not associative. That actually takes a little bit of work to make things not associative. Okay. So these grammars, we're already up to 3 productions to get 3 levels of precedence: addition, multiplication, and grouping. Okay. All right. Now, let's see. This is almost what we want here. Actually, if we think about addition and multiplication, they're like this one makes addition is left associative, and multiplication is, the term is right associative. So multiplication is right recursive. Usually we would want addition and multiplication both to be left associative. Okay, so that would be okay. See, there's 3. This one's left, right. This one's right, left. Then they're both left, and then they're, let's see, did I do both right? Okay, I did 3 out of the 4. I made one left, one right, then the other one right, and the other one left, and then made them both left, which is the one that we really use. And I didn't do the one for making them both right recursive. Okay. Notice that iteration, to make them both left associative, expression is not recursive. See, it's iterative. Okay. And then term is not recursive, it's iterative. And then factor, finally, actually, you don't get the recursion until you get down here to factor. Factor takes you back up to expression. So expression immediately calls term, term calls factor, factor calls expression back up. So they kind of go in a circle like this. But then there's iteration in between. So expression calls term, and then it iterates on a while loop while there's more tokens, plus term, plus term, plus term. Okay. When you call term, term calls factor, and then when factor is brought back as factor, then term iterates on times factor, times factor, times factor. So while there's more tokens, while factor, while factor, while factor. Okay. So call term, then iterate, call factor, then iterate, and then factor recursively calls expression. Okay. Oops. Now, over here, see, now there's a parser here for language 25. So let's go back to 25. Let's see, what time do we quit? I lose track of time.
I think it's supposed to be 3:15.
Oh yeah, nobody stopped me. Yeah, so we should quit. Yeah, we'll pick up here on Wednesday. We'll look at the parser for 25. I didn't even see. I wasn't looking at the clock. Yeah, tell me when it's time to quit. Unless you're having fun. Okay, so we'll meet again on Wednesday. We'll pick up where we're going to look at. We want to look at the actual code for one of the parsers. We'll look at the parser for 25. There's going to be another program assignment up there in a couple. I hope maybe by Wednesday there'll be another program assignment up there. And if you have questions, send me emails. We can also do questions by Zoom. If somebody has a question, I can always meet you, like talk with you over Zoom, and stay in contact with each other. I think I wrote you an email. There's tools you can use to, you can even program together. You can work with people. You can work with other people over distance, remotely. And does anybody have any question right now? Okay. Oh, and these examples that we did here, I'll save them and I'll put them up on the website. We did these little parsing examples. I'll save those and put them up on the website. Okay. And any questions?
No.
Okay.
I
So
don't
I'll go
think
ahead
so.
and end the meeting. And next time, if I get carried away, feel free to let me know. All right. Okay. Now I have to figure out how to stop the meeting. Okay. All right, got end meeting. Okay. Goodbye. See you in a couple days.